Hello, welcome to the group meeting, and today's seminar is going to be Wurtz. How do you pronounce it?
Wurtz.
Wurtz.
Like Hertz, but with a W.
Okay, and she's going to talk about accelerating the search for action in dark matter with entangled cavity states. Ooh, nice. All right, where is yours?
Thank you. All right, hi everybody. Thank you guys for being here today and giving me the opportunity to talk about some of my past research. I'm going to share today about the research that I was a part of at CU Boulder for the past few years, which is research in quantum metrology or quantum measurement for Axion searches. This research has nothing relativistic about it. However, I will be talking about a type of particle detector. It will not look very familiar to, or look very similar to the type of particle detectors we usually talk about here. I was initially interested in this research when I joined this group because I had an interest in particle physics at the time. I quickly found out that this is not at all research in particle physics, but this did lead to my interest in how studying the physics of information can lead to new insights in fundamental physics. And from my perspective, quantum metrology is a way of studying information, but instead of thinking in terms of entropy or channel capacity or resource theory or things like this, information in quantum metrology comes in the form of signal and noise. And what makes quantum metrology interesting is that you're operating in a regime in which the primary source of noise is sourced by vacuum fluctuations. And as we will see, it's actually quite important to figure out how to evade the noise from vacuum fluctuations. And today I'll show you how we do that. So you don't need to already know anything about what an axion is for this talk. I'll start off by introducing the motivation for the axion, as well as how we aim to detect them. And then I will talk some more about quantum noise, what the sources of quantum noise are, and how we can further increase the sensitivity of our detectors when our primary source of noise is quantum noise. The cavity entanglement and state swapping concept is the novel part of this research, and this is a method of increasing the sensitivity of axion detectors by generating entanglement and state swapping interactions between two resonators. That will make sense later. And finally, the best part about doing theory for an experimentalist is that the thing that you propose actually gets made. And so I'll share some finally about how this experiment is currently being brought to life. By the end of this, we'll know what we're looking at in this picture here, but for now it's mostly just here because it looks cool. So let's get to talking about axions. The axion is a hypothetical particle motivated by a problem in QCD called the strong CP problem. And this problem has to do with symmetries of the Lagrangian. As you may be aware, some of the symmetries that particle physicists look for in particle interactions involve charge conjugation symmetry and parity inversion symmetry. They want to know, do the laws of physics change when we flip the charge or the parity or both together? Electromagnetic interactions, for example, will preserve either one or both of these symmetries together, the so-called CP symmetry. But the strong and weak forces have a term in their Lagrangians that allows violation of CP symmetry. And the degree to which we expect the CP symmetry to be violated is determined by this constant parameter theta. Like many parameters in the standard model, we're not told the value of this parameter. We have to measure it experimentally. So performing experiments on weak interactions by looking at kaon decay, we find that the value of this is non-zero. It can take any value between 0 and 2 pi. And we find that in weak interactions, it is non-zero, and thus that weak interactions do not preserve charge parity symmetry. For strong interactions, we can look for CP symmetry violation by measuring the electric dipole moment of the neutron. Here I've just drawn a rough little picture of how that works. And what we observe is that CP symmetry is actually perfectly conserved, or at least we've measured theta to be within 9 decimal places of 0. And this may sound fine because, again, it's allowed to be broken. It's not necessarily required to be broken. But when theta could take any value between 0 or 2 pi, and we measure it to be almost exactly 0, that is a naturalness problem that demands motivation. It points us towards some mechanism that we're unaware of that's causing this symmetry to be conserved. So in 1977, Roberto Peche and Helen Quinn postulated that this parameter theta is not a constant, but rather a dynamical field that has a stable point at 0 and thus naturally relaxes there. And the creation of this new field implies the existence of a new particle, which was called the axion after a brand of dish detergent for cleaning up the theory of QCD. And various experimental constraints have constrained its mass to roughly the micro EV to milli EV range, though sometimes there are ways to get around these bounds. So the parameter space is a bit larger. But we expect them to be very light, and due to their small mass, in addition to the fact that they are chargeless and bosonic, allowing them to have an arbitrarily high mode occupancy, they've become a leading candidate for dark matter. And we know several production mechanisms in early universe cosmology, which would create an abundance of axions, enough where 100% of observed dark matter could be explained through this generation. And so the axion is now getting a fair amount of attention. So it is a leading candidate for two of the most prominent questions in particle physics, the dark matter problem and the strong CP problem. But the fact that we don't know its mass a priori is a huge obstacle to detecting it. And to explain that, I'll introduce the general principle that axion searches work off of. So axion detection is based on the principle that if axions exist, they exist all around us in abundance, and off the fact that they can convert to photons when they're in a strong magnetic field. And if you're thinking that you thought dark matter doesn't couple to the electromagnetic field, that is a fair thought. And how this works is axions have a direct coupling to gluons, and through gluon mixing with the pion, that leads to an axion photon coupling. And that's about all I can say about that. But specifically, they will convert to photons that have the same frequency as the axion field, or in other words, the energy corresponding with the rest mass of the axion. And in one type of detection scheme, we create about a 5 to 10 Tesla magnetic field with a big expensive solenoid. And inside that field is an electromagnetic cavity. In the device of the haystack collaboration, this cavity is a copper cylinder shown here. It's about the size of a 2-liter beverage bottle. And we have a port on the cavity in which we can stick a wire to probe the electromagnetic fields in the cavity. This device is called a haloscope because it's designed to probe the galaxy's dark matter halo. And if the resonance frequency of the cavity matches the frequency of these photons being generated by the axion field, then the cavity acts as kind of a trap and allows a signal to build up as more and more energy enters the cavity from this axion to photon conversion. And the result, what we would see at the output, is a slight but persistent excess in the variance of the cavity's electric field in a very narrow frequency band. So in this sense, a haloscope kind of works like an FM radio, where we're tuning the resonance frequency of our detector with the aim of picking up on some signal that's already out there, but we don't know its frequency. And so you may already recognize that one of the difficult factors here is that we don't know the frequency of the axion field. And thus our cavity has to have a tunable resonance frequency so that we can scan through frequencies in discrete tuning steps, integrating power at each step, looking for some signal to rise out of the noise. And the main figure of merit for a haloscope search is the rate at which we can scan through frequencies. So we can think of the scan rate as being determined by two things. First, how sensitive the detector is to an axion signal while it's sitting parked at some frequency, because this determines how long we have to wait integrating power to be able to resolve an axion signal. if it is near the detector's resonance. And secondly, the scan rate is also determined by the bandwidth of the detector, because if the detector is sensitive over a wide bandwidth around cavity resonance, then we can take bigger steps through frequency space and scan through the parameter space faster. Okay, are there any questions on anything so far? I forgot to say you guys can interrupt me with questions at any time.
So I have questions, but they're more like longer discussions. So maybe for me, it's best to leave them at the very end. Maybe a quick one though, is that it feels a bit funny. So when you talk about the frequency of the action, what do you mean by the frequency of the action?
Sorry, axion.
Axion, sorry, my bad, yeah. What do you mean by the frequency of the axion?
The frequency of the axion would be whatever the axion's rest mass is. You can find the frequency of the photon it would convert to just by like MC squared, M axion C squared equals H bar omega.
So it's the mass of the action you're referring. We don't know the mass, and therefore we don't know what the decay process, the scattering energies of the decayed products are. Is that it?
Right, yes.
Okay, gotcha.
Okay, cool. So this all seems easy enough. Now that we know how the experiment works, we can begin to understand its limitations, and its limitations have to do with quantum noise. So first of all, when I talk about the axion signal manifesting as a slight excess in the variance of the cavity's electric field, we need to talk about how the scale of how small that variance actually is compared to vacuum noise. We've effectively eliminated all noise that we can eliminate from a thermal level because we operate at 10 millikelvin in a dilution refrigerator. So we're really just dealing with the vacuum fluctuations of our experiment. And the power that we receive from these vacuum fluctuations at the output overwhelms the power that would be generated by an axion signal by about 3 orders of magnitude. So this research fundamentally is a question of how do we search for a signal that is so weak that by an overwhelming margin, our primary source of noise is the noise of vacuum fluctuations. And this is the task of quantum metrology. And so this is where I bring in the analogy of the Princess and the Pea, which, as you probably know, is a story about a woman who is tested for her sensitivity by being asked to sleep atop a big pile of blankets and mattresses. Unknown to her, underneath all these is a single pea. And when she wakes up in the morning, because she is sufficiently delicate and sensitive enough to be a princess, she finds her back to be very sore from this pea. Now, compared to somebody who is trying to detect the axion, she has it easy because she just has to lie on one pile of mattresses for one night and determine if there's a pea there or not. And in fact, if we wanted to sit at one frequency and determine if the axion is there or not, we can do that too. We just collect the energy coming out of the cavity for a few hours. And if there is an axion signal present, we would see a sharp narrowband signal rising out of the quantum noise, which is our equivalent of back pain. However, we don't know the frequency of the axion. And so we have many different frequency bins to do this with and search through.
So again, I'm gonna, okay, no, go forward, because maybe that answers my question. Go to the next slide. Yeah, and maybe you're gonna talk about it. So here's the right, look at that. The mass of the action in that axis is tiny. So when you talk about the frequency of the action, is it because of the energy that it comes with, as in like the fact that it's an excitation coming from some process? So I guess to detect an action, you have to think of a process that produces it, which is the Primakov effect here, no? Mm-hmm. And that would give you some scattering amplitudes for some frequencies, some distributions in frequencies, right? And that assumes that there's some incoming energy and then outgoing energy. Is there outgoing energy that's not known? Because it doesn't feel to me, or is it just the mass? And the mass is tiny, tiny, tiny here.
I'm not sure I understand the question.
So the mass range here on the x-axis, you have 10 to the minus 12 and 10 to the 7. This is a huge range. But you also consider that the mass could be really, really small.
Yes.
There's electron volts. So are you assuming, so the detection that you have a detector. But typically to detect light, you point at a source For example, I want to detect light from a distant star, so I point at a star. The Primakov effect does not happen equally in all media. Primakov effect requires some scattering amplitude, and that scattering amplitude will depend on the process that you're considering. So typically, you want to point your detector to a source, right?
So what's our source?
So that's question one. What's the source? And second, in that process that produces the scattering products that you want to measure, what is the comparison between them? So is the action ultra relativistic? Is the action not? So is the energy of the scattering, if you want, is PC much larger than MC squared in this or not? Do you know anything about that? Are you looking for effectively a massless particle, and then the frequency that you call of the action of the axion, sorry, the frequency of the axion, I keep doing that, is determined by the if you want the kinetic energy of the protons, let me call it kinetic energy, or is it determined by the mass? Really, it's really a ultra non-relativistic for the frames that you consider particle that MC squared would dominate, and that confuses me because when I see this x-axis, it could be either or, I guess. So those are the two questions. What's the source, and then what is the typical energy, not from the mass, that you expect from those products to come in?
Yeah. So at least the detection principle with cavities for the QCD axion is based on the inference from axion theory that if axions constitute most of the dark matter of our universe, because we know they are so light, we know that they would be ubiquitous. We're basically swimming in a sea of axions, and we know that in a strong magnetic field, these axions would convert to photons. And so we operate under the assumption that they are already everywhere. And when we put in our big 9 Tesla magnet, that we will get axion to photon conversion.
I see. So you stimulate, so you give it the conditions for the process to happen, assuming that there's axion excitations everywhere. Is that it?
Yeah.
And the mass is so tiny, you said, but then in the x-axis, you have a range from really, really huge masses. I mean, bigger. Here you have of the order of several mega electron volts, right? 10 mega electron volts on one extreme, and you have a peak of electron volt on the other hand. It's because, so is there an assumption about the mass? I mean, because you said the mass is so tiny.
Yeah. So to answer your second question from before, we also we assume that axions are cold dark matter, and so what this means, they're not moving at relativistic speeds compared to our detectors. So nothing relativistic here. So we really are just trying to detect the energy of their rest mass. And as you noted, it's very small, and this is why we only get a signal 1,000th the size of vacuum fluctuations, even when we have a big cavity.
Right. So, but then why isn't this plot the mass to be such a big range? If there are there fundamental reasons to think the mass is small, and why this plot has masses of 10 mega electron volts?
So here, I mean, when I mentioned before that the mass was constrained, well, basically to this region, I said micro electron volts to milli electron volts. That is taking into account the exclusions that have been done with the observational or observations that are plotted here. And this, I'll talk about this in a moment, but we basically expect that the axion lies on this line in this parameter space. In other words, has a axion photon coupling that's proportional to its mass. And thus, like, this is kind of the region of parameter space that we are now focusing on searching.
I got it now. Thank you for the explanation. There's something about it, because I guess the assumption that is a cold, a non-relativistic, if you want, or deep non-relativistic with respect to your experiment, right? It's an assumption coming from the fact, well, let's assume that it's dark matter. If it's dark matter, the only thing it can be is cold dark matter. So therefore, let's assume that as component of dark matter, it would be non-relativistic with respect to my experiment. Is that right?
I guess so. I'm actually not sure.
Because with that mass, anything can be very relativistic very fast. See what I mean? With that mass, it's very easy. So we're talking smaller mass than an electron. And electrons in strong magnetic fields quickly become relativistic and even ultra relativistic. So that's why there's an assumption here that it has to be cold dark matter, right? And then finally, and the last question, sorry about that, is the vacuum fluctuations that you talk about from the axion field, or is it from the electromagnetic field associated with your detectors? Because typically, go ahead.
We will get into that.
Gotcha. Then. Keep going.
Yes. Yeah, you'll hear lots about where the various noise comes from after this. Okay. So yeah, our other problem, in addition to the fact that we're only getting a signal that is 1,000th the power of vacuum fluctuations, is that this frequency space is enormous. It's way too big for our current technology to scan in any reasonable time scale. To get a sense of this, if the axion were to have a mass in the 1 to 10 micro EV range, this would manifest as a 1.5 to 15 gigahertz signal. But to scan the 1 to 10 gigahertz frequency range with our current technology is estimated to take over 20,000 years of continuous detector lifetime. And obviously we don't have time for that. So this exclusion plot shows everywhere in axion parameter space that we have determined there is no axion, where on the x-axis we have the axion mass, and on the y-axis the axion photon coupling. There are a lot of astrophysical observations, as I mentioned, and experiments that rule out axions in these areas of parameter space, especially where there is a large mass or strong coupling. But this band in yellow is where two benchmark axion models predict the axion to lie. We expect that its mass will be proportional to its coupling. And this region is where cavity experiments operate. This is the region that would take 20,000 years to scan through with current technology. So theoretically, people who say that we are capable of detecting the axion with cavity experiments any day now, and I have heard people say this, they're right, but in practice, unless we get extremely lucky, we are not close to discovering it yet. We, in reality, need some technological advances that are going to allow us to search comprehensively through this parameter space on human timescales.
Kelly, how do you get the 20K years here?
This is, yeah, I guess I should have cited that too. This is a calculation that somebody I worked with did just based off of the scan rate that we currently have with detectors limited by quantum noise.
But imagine that I have 200,000 detectors. Would that mean that it would take 0.1 years? So, because I don't know how that amount is arrived to. Maybe it's a single experiment continuously running, but I can have.
It is, yeah, with one single experiment continuously running. If you wanted to have 20,000 detectors, you would need 20,000 9 Tesla magnets and a lot of money to get.
Yeah, okay, but it's like that. No, I could increase the number of detectors. Okay, gotcha.
Yeah. Okay, yeah, and that's just this small range here. And it's worth noting that it is very much worth searching through this parameter space, whether we find the axion or not, because if we search the whole space and we don't find anything, we'll have ruled out one of our leading candidates for dark matter and the leading solution to the strong CP problem. So that would also be a very significant non-discovery. Okay, we've discussed how the spectral scan rate depends on how sensitive we are at each tuning step, as well as how large the detector bandwidth is. In other words, how big the tuning steps we can take are. So to increase the scan rate, we need to improve one or both of these things. And to look at how we can do this, we're going to look more closely into the sources of quantum noise and how they behave. Okay. I recognize that breaking down various sources of noise in an experiment may not sound like the most attractive, exciting thing to theoretical physicists such as yourselves, but remember here that noise is synonymous to quantum uncertainty when we're just dealing with vacuum. And we're going to break down exactly how the uncertainty in our experiment behaves, because once we can understand that, we can begin to play games with the uncertainty principle and exploit it to our advantage. So first, we need to understand exactly what we're talking about when we say noise. So coming out of the cavity, along with any potential axion signal, is the noise generated by the vacuum fluctuations of the cavity itself. This noise, which I'll call cavity noise, has this frequency dependence around cavity resonance, where the y-axis can just be thought of as how much power we're receiving at the output for a given source. And at the bottom here, I've plotted 3 possible manifestations of an axion signal, which may come with this noise. While the axion signal would be much more narrow band than the cavity, the thing to note is that the power we get from an axion signal at any frequency, shown here by this green dashed line, has the same fall off behavior as the cavity noise. And this would mean that the axion signal always comes in fixed proportion to the cavity noise, wherever it is with respect to the resonance frequency of the cavity. But if you think about that, that would mean that we can achieve the same signal to noise ratio at any frequency, or in principle have an infinitely broadband detector. So what are we missing here? What we're missing here is the vacuum noise that comes from outside the cavity, which basically has the inverse frequency dependence. And to show exactly where this noise comes from, I'll show a part of a circuit diagram of this setup, where we have our cavity, we have a circulator, and our amplification chain. And I'll first explain what the circulator does and then why we need it. So when signal from inside the cavity exits the cavity, the circulator transports it from the port that it goes in to the next port in the direction of this arrow. So the signal from the cavity is directed out this way towards the amplification chain, which is represented by this triangle. And then we read it out further up the chain. However, the reason we need the circulator here is because the amplifier produces a lot of back action, which means it's basically shooting super large amounts of noise out the back of it. And to protect our signal and cavity from this noise, we have the circulator here to direct that noise to a resistor where it is absorbed. But we can't get rid of this noise completely, or we can't get rid of all noise from outside the cavity completely, because this resistor is generating vacuum fluctuations, and the circulator will route those vacuum fluctuations back towards the cavity. And so that noise comes in and is reflected off the cavity and joins our cavity noise and axion signal, where we will read it out. And basically, no matter which way you set the circuit up, the vacuum noise associated with measurement, minimum vacuum noise associated with measurement, is unavoidable. I find it helpful to think that our circuit is basically connected to a bath somewhere, and the temperature of the bath can never be below vacuum. And to get anything outside of our cavity, we have to expose it to the bath. So this noise, which we'll call measurement noise, on cavity resonance will just enter the cavity and be dissipated by the cavity's internal loss. But off resonance, it will reflect off the port that we're measuring our cavity output from and pollute the axion signal and cavity noise. So now that we know exactly where this quantum noise is coming from and the nature of these sources with respect to frequency, it would be helpful at this point to define quantitatively how sensitive the detector is as a function of frequency. And this is done by the visibility, which is defined as the power we would get from an axion signal over the total power from signal and noise at the output. And by power, I mean power spectral density, technically. Because the axion signal is so small compared to the noise, this is basically a signal to noise ratio, but it's defined in this way because this is the quantity that directly comes into the expression for the scan rate. The scan rate is proportional to the integral of the visibility squared. And what is defined as visibility here and in the literature is basically what I was colloquially referring to as sensitivity before this. It made sense intuitively that to increase scan rate, we'd need to either be more sensitive at each step, making like a taller visibility curve, or have a wider bandwidth of sensitivity, a wider visibility curve. And here we see that reflected in the integral of this quantity called the visibility. So now that we have all this machinery set up, we'll begin looking at how we can increase the area under the visibility curve, thereby increasing our scan rate using quantum squeezing. So as we said, the visibility is basically a signal to noise ratio. And remembering that cavity noise gives us a constant ratio, we can see that, well, cavity noise gives us a constant ratio, which will basically be our maximum visibility. And measurement noise is minimized on resonance, so we will achieve that maximum visibility on resonance. And then as we go off resonance, measurement noise begins to be reflected, and that causes the axion visibility to fall off. The characteristic bandwidth of this visibility curve can roughly be thought of as the bandwidth here that the cavity noise is dominates over the measurement noise. So how can we increase the integral of this curve, therefore increasing our scan rate? And I'll say again, this curve is essentially telling us how sensitive our detector is and over what frequency bandwidth it sustains that sensitivity. Okay, so how can we make this bigger? This is where quantum squeezing comes in. So I'm going to show a phase space representation of the measurement noise coming from outside the cavity. We can think of this as like just before it reflects off the cavity. But instead of position and momentum here, we represent signals in terms of their X and Y quadrature components, which can be thought of as the sine-like and cosine-like components of the signal. And this blob here represents vacuum noise, which without our intervention will manifest equally in each quadrature. And the uncertainty principle basically tells us that the area of this blob cannot be smaller than it is right now. However, it turns out that you can prepare the noise outside the cavity in a squeezed state, where the variance in one quadrature is reduced at the expense of increasing the variance in the other. And so that would look like this. And if we prepare the measurement noise in a squeezed state, and then perform a phase sensitive measurement upon this squeezed quadrature, in other words, we only measure the X component of the signal, then we decrease the measurement noise with respect to the cavity noise and axion signal, thereby increasing the bandwidth of sensitivity. And my rough little sketches and animation here don't exactly show that the integral of this curve is doubling. However, this concept was tested in Boulder prior to my arrival there with a fake axion signal. And when it was shown effective, it went to the real Axion search of our collaboration, which is at Yale, and was implemented in an actual haloscope in early last year. And the result is carving out a bit more of this exclusion plot, but this time doing it 2 times faster than we would be able to scan without squeezing measurement noise. And this is enough of achievement for a Nature publication. Okay, does anybody have any questions on this stuff? I need to sip water. Okay. So while this was all going on, we already needed to be thinking about how can we do this even better, because 10,000 years is obviously better than 20,000 years, but our job is not done, and we need to see if it's possible to take this further if we want to have hopes of detecting the axion. It turns out that with this method, further scan rate enhancement than has already been achieved is limited due to the fragility of these single mode squeeze states and how easily the squeezing can be degraded by even a little bit of noise being added as the state is being transported around the circuit. So here's another idea. What if, I'm just going to undo what we've done so far and get rid of this. What if we found a way to amplify the cavity noise and the axion signal together before they exit the cavity, and are polluted by measurement noise? Sorry. The If we can amplify the axion signal and cavity noise together within the cavity, then the bandwidth increase that we can achieve is limited only by the amount of amplification that we can achieve. But how are we going to do this? And the answer is with entanglement and state swapping. So let's talk about this idea. I'm going to now very qualitatively introduce the idea that by using two cavities, our axion cavity and some additional auxiliary resonator, we can amplify the axion signal before it is polluted by the noise introduced by measurement. So our axion sensitive cavity has resonance frequency omega A, the second cavity has resonance omega B, and the states of each cavity can be represented by these blobs of quantum noise and phase space. And so we'll join them together through an element that can be driven at some rate to vary the coupling between the cavities. And this driving this thing basically just means that we're going to modulate its inductance in a nonlinear way that generates certain desired interactions between the modes. So if we drive this at the difference frequency of the two cavities, we enable a state swap interaction under which the cavities will continuously swap back and forth. The cavity states will continuously swap back and forth at some rate that depends on how high we turn up the power of this drive. But if we instead drive at the sum frequency, this creates a two-mode squeeze state. In other words, we both entangle and amplify the cavity states to create an EPR-like state where there are correlations between the quadratures of one cavity mode with the other. And if we apply both of these interactions at the same time, this is where the magic happens. If we do this, then the cavity states in phase space look like this. And this tells us, for example, this is our readout cavity state. If we were to only read out if we were to only make a measurement upon the X quadrature of this readout cavity, we would see nothing but vacuum noise. But if we were to measure the Y quadrature, we get exactly what we hoped for. The noise originating from the resistor, the measurement noise, remains unamplified. This is still just vacuum noise. While any cavity noise and any potential axion signal is amplified far above it. And to understand exactly why this happens requires either input-output theory or just a very good intuition for quantum optics. But some intuition that I can give, recall how with this idea of squeezing the measurement noise that's being reflected off the cavity, the first idea, we're using the fact that unwanted noise is decreasing in the measured quadrature. Here, we're using the orthogonal component of squeezing, which amplifies noise, this time the noise that we want because it comes with an axion signal. Two-mode squeezing is a bit confusing because with two-mode squeezing, the squeezing doesn't happen in one state or the other. It happens in a kind of joint basis of the two modes. And when you add state swapping to that two-mode squeezing at precisely the correct rate, it kind of undoes the entanglement in such a way that the amplification of the noise we want is still preserved. And the crucial part about this is that the cavity noise in our axion signal is amplified before it exits the cavity system and is polluted by the noise introduced by the resistor. So hopefully this made some sense. If not, it's okay. This took me at least 18 months to understand. But while these concepts may be more concrete than we're used to talking about in theory land, this is still a bit abstract for experimental land. And to come up with a prediction for scan rate enhancement, we definitely need to get a bit more concrete. But first, every legitimate proposal needs a clever acronym. So I will be referring to this concept as ceasefire, the cavity entanglement and swapping experiment for improved readout efficiency. So how do we get the ceasefire scan rate enhancement? This would be the part, sorry, this slide is so messy. This would be the part where it would be appropriate for me to now go through all the math of how we did this model, but I've given everyone a lot of probably new information and you may be too bored or tired for a lot of math right now. So I'll refer you to our paper for that, but I'll basically explain how this model works and present the quickest calculation I can that easily reveals how when these interactions are combined, they produce the amplification pictured here that we desire. So our two-mode model in the visual language of microwave engineering is drawn like this. This system is completely parameterized by only the bare resonance frequencies of each cavity, as well as the rates that the cavities gain or lose energy through various mechanisms, which are modeled as ports, with loss rates given by kappas. So these two ports here are fictitious ports. The coupling to the Axion field is modeled by a port with a generator on it. The cavity's internal loss is modeled by a port with just a resistor. And then we have the measurement port over here, which is a real port, and how we're reading out the fields from our cavity system. G is the rate at which the cavities are swapping states, and H is the rate of two-mode squeezing. We can simplify this and get rid of all the circuit garbage by just representing it as this input-output theory schematic here. This is kind of the most idealized picture of this system, and basically all we need to know about the system from a theoretical point of view. The Hamiltonian of the system is given here, where H0 comprises the bare cavity Hamiltonians, and then we have the state swap or beam splitter interaction Hamiltonian and the two-mode squeezing Hamiltonian. And while I have the Hamiltonian written here in the field operator basis because it's easier to write that way, but if we were to transform this to the quadrature basis and find the Heisenberg-Langevin equation of motion for the y quadrature of the readout cavity, setting H equal to G because that is just what is optimal to do in the end, we find that it is mapped, the change in the y quadrature of our readout cavity is mapped to the x quadrature of the axion sensitive cavity with amplification that scales with this rate G. And so what this means is that any axion signal that manifests in the x quadrature of the readout cavity will be amplified into the orthogonal quadrature. Any axion signal that manifests in the x quadrature of the axion cavity will be amplified into the orthogonal quadrature of the readout cavity. And that is what gives us this amplification that we've been wanting. So this rate G, if everything depends on the rate G, what limits G? All I've said is that this rate goes up the higher we turn up the power on these drives. And that's true for both G and H. And the hardware that's involved in generating these interactions is where we get the limits of this technique. But judging off of the technology we have available and the swap rates that we predict to be achievable, we can determine what we think the achievable scan rate enhancement over a standard haloscope, not using any form of squeezing, would be. So the y-axis of this color plot is basically us turning up the power on these drives generating the interactions. And for any achievable interaction rate that we can get, there exists an optimal level that we can set the measurement port coupling to achieve the maximal scan rate. And we're parameterizing these results in terms of the loss rate of the axion cavity. So these predictions are valid independent of that. So the rates that we predicted are achievable, and the corresponding optimal measurement port coupling are marked by the white circle in the upper right corner here. And I can go into how we derive these rates if anybody really wants me to, but I won't do that now. So with these parameters, we expect that the visibility bandwidth will have the increase shown here over a standard haloscope, which corresponds to a 15-fold increase in scan rate. And that is really the upshot to this paper we just put out and to all the research that I've done at Boulder. This looks like a very promising improvement to the search for axions. And the coolest part is that it's actually getting made. So these are pretty outdated pictures, but this is what a particle detector looks like in the axion world. What's currently being built is a test demonstration of the ceasefire concept. There is no big magnet at Boulder. And so the system is tested with a fake axion signal put in by a signal generator, and then a whole analysis is performed as if it were a real axion search. And if and when that is successful, possibly in 2 years or so, then it will start being built into the actual haloscope of the Haystack collaboration, which is at Yale. And if all goes well, then used to carve out some more of the axion parameter space. This is the inside of a dilution refrigerator. This is the whole part that gets very cold. This is the part specifically where my tiny cavity is. I don't need to have these special cavities that are engineered for real axion search just to test things here. And this was the cavity device I was using, where these are the two cavities that we kind of swap things between and entangle. And then this is a mess of all the signal generators and everything that we probe into the dilution refrigerator with. So I introduced a lot here. So to recap, the Axion is a leading candidate for dark matter and the leading candidate to the strong CP problem. So there's a big motivation to try and detect it. However, we're ill-equipped to do that with current technology because the parameter space is so big and the Axion signal is so weak. But quantum metrology can come to the rescue by employing quantum squeezing in our readout techniques. And there's been a method of squeezing already employed by squeezing the noise external to the cavity. And this has been successfully implemented in an axion search, and it results in a doubling of the scan rate. But we expect that further progress with this technique is hindered by the fragility of single mode squeeze states. But if we employ the ceasefire method, which uses state swapping and two-mode squeezing to amplify the cavity noise and axion signal before they exit the cavity system, we can get a much greater bandwidth increase that could result in a 15-fold increase in the scan rate enhancement. And I will note that it's possible to maybe use these two methods together to maybe multiply the scan rates that we could get with either one, but we have not looked into that yet. Now we may recognize a few things in this illustration. This was just something done by the in-house graphic design artist that Jilla has at CU Boulder. And he made this as a proposal for Nature to use as their cover art for that squeezing technique that they published. And they didn't use it, but this is still a pretty cool picture. These are axions streaming into our copper cavity, and these metal squares are the devices that squeeze the quantum states, which are pictured flying to and fro here. So anyways, this 20,000 years number is definitely still really long, even when you divide it by 15 or 30. But one of the main takeaways, I think, from this proposal is that a comprehensive search of this parameter space is possible if, and probably only if, we improve our readout technology using techniques from quantum metrology. And it looks like those techniques can actually significantly help us. So that's all I have to say. Thank you guys for listening.
Thank you, Kelly. Very nice. So really nice talk. I really liked it a lot. Very well explained and very nice. I have a ton of questions. So it's really cool. One of them is more philosophical. That's the one I was saving for the end. So before getting there, so when you inject fake axion signals, you don't have the magnetic fields on at all, right? You don't have a strong magnetic field there.
Correct.
Do you expect, because if you were, for example, a photodetector, a regular one, just a regular photodetector, photo multiplier, something like that, will be strongly affected by 9 Tesla, as in like you displace the spectral lines and then you move the resonance around. I wonder, does the fact that these detectors are subject or have close by strong magnetic fields affect the measurement, or are the magnetic fields constrained and not affecting the detectors in space? Is that something that worries people?
So the biggest effect of the magnetic field is that metals can't superconduct in a magnetic field. And so this is the reason why our cavity really has a loss rate at all. If you notice, I didn't include a loss rate for the readout cavity because that's allowed to be outside the magnetic field. We don't care about axion conversion there. And that cavity can superconduct and it effectively has zero loss rate. So the fact that the cavity is in a magnetic field is what introduces its loss, which is harmful to us because it can't build up as big of an axion signal the higher its loss is, but we need the magnetic field, so we can't get around that. In the ceasefire concept, it's important to have this modulated inductance element outside of the magnetic field as well, because the inductive element is an element called Josephson junctions, and those rely on superconductivity to operate. So that has to be removed from the magnetic field too. But we can null the magnetic field about 50 centimeters away from the cavity. And so the magnetic field really only affects the cavity physics, the axion sensitive cavity physics.
This is interesting because you have an atom, right? You have two regimes if you want that are easy to compute the effect of, well, computing can be done anyway, but the effect on an atom of strong magnetic fields, you can go to the Zeeman extreme, which is when the magnetic field effect, the energy, that the energy splitting that you cause with the magnetic field is below the LS coupling. So it's small as compared to the LS coupling. And there's the other extreme, which is the strong stream, but that is 10 to the 5 Tesla or so, which is close to a neutron star, but the atom is disintegrated. Now, here, it's in the middle, you know? I mean, 9 Tesla, 10 Tesla is typically not Zeeman, in the sense of Zeeman would be, the splitting is huge. So you split for an atom in there, the spectrum of that atom would be split in funny ways and new interference and so on. But that's not affecting your detector, right? That's what you're telling me. It's just that the cavity gets superconductive and that's it.
Yeah, are you asking about, say, the atoms like in the cavity walls?
Yeah, I mean, the sensor is made, in the end, you're detecting photons, no? You're detecting light.
Yeah.
And the detectors of light, which is made of matter, typically is the multiple structure and typically the dipole structure of atoms. That's what we model with Andrew DeWitt, for example, simplifying a lot. But in the end, for example, a very primitive detector is a photomultiplier. You have a single atom that detects it, and then when there's a decay, you amplify the signal by creating a cascade of electrons coming from other atoms. But all those things are extremely sensitive to strong magnetic fields. That's what I mean. So I wonder what the photodetector is like, and maybe you just tell me, no, the photodetector is outside the magnetic field region, or I don't know. I wonder.
So how we're probing the electromagnetic fields inside the cavity, we don't have anything like a photodetector. It's, I mean, basically a hole in the cavity with a wire stuck into it, and how far that wire is stuck in determines the coupling rate, how fast we're like receiving energy from inside the field. So that's all. But
the sensor is outside of the magnetic field. No? Whatever makes the detection of the light is outside of the magnetic field. Is that what you're telling me?
No, it's still within the magnetic field because the whole cavity is within the magnetic field. And basically the EM waves in the cavity will create a signal starting at this little pin that we stuck in. And so that's also in the magnetic field. But I think the only effect of the magnetic field there for like our circuit is that part can't be superconducting and thus is like more lossy than normal.
I guess the pin, what's it made? So how do you detect, how do you go from an electromagnetic signal to something in the screen of the computer, right? Like that's.
Yeah, that's just the.
What is the detector made of?
Gold-plated copper.
Right, so it's an antenna in a way. It's a radio antenna.
Yeah.
Okay. Oh, a radio antenna is a giant dipole. Although I don't know. Yeah, maybe the effect of the magnetic field is just an offset because it acts as a superconductor. I don't know. Again, just saying that typically, no matter what detector you use for electromagnetic fields, they're not insensitive to strong magnetic fields. But I assume these people obviously know because they work with this stuff every day. So.
Yeah,
it's more me being curious as to why that's not a problem, because 10 Tesla is not a small magnetic field. 10 Tesla screws up many things.
Yeah,
typical assumptions that are made in atomic physics and things like that.
I mean, probably just that our relying on like one atom to discern properties of this electric field. It's an actual like macroscopic item that is.
Oh yeah. But photodetectors, for example, cascade photomultipliers are macroscopic objects that still are subject to the modification of the internal spectrum of the atom, because in the end, it's more that a signal is detected locally, like a single atom detects something and generates a process in cascade. But it doesn't matter. This was just me being curious about realistic detectors. Antennas will stop working in strong magnetic fields too. So an antenna, if you have a strong magnetic field, the antenna will stop working. The physical properties of what makes the antenna an antenna would start not working. It's like a big atom in a way. But anyhow, whatever. This is maybe not the question to ask you here. I get it's not a problem. The answer is no. Nobody cares about the how magnetic fields affect the
answer is nobody cares, but yeah, I'm not sure.
I have a more philosophical question about the axiom. So this is something interesting because it makes you think how much of the physics we do is very anthropic, in the sense of how much our human experience and expectations affect what we have. This is my understanding that for the axiom is very Gelmaniac, in a way they're saying, right, the natural term has this theta, and the value theta equals 0 or very small compared to 0. It's very fine-tuned, and that's why we don't like it. Yeah. Gelman said this thing: if something could happen, it will happen. You know, that thing. If something has a small probability of happening, it will happen. Meaning, like, it's just us not liking two possible things, right? One is that the value is actually very close to 0 in the model, and there's no violation. So in the natural model. Second, the natural model may not be good enough. And restoring it with at the symmetry with an axion field, which is something very simple to do, may not be enough to actually get the right model. So I wonder why people don't get discouraged, right? It's the same happened with supersymmetry. Supersymmetry is something that people kept insisting until the last, even though it wasn't found, even when the hope of being found, it was very small. If you go to particle physicists, they were still, you know, like clinging to, oh no, there must be supersymmetry.
The string theorists are still clinging to supersymmetry.
Well, I mean, there's no string theory, there's no M theory possible without supersymmetry at some level. So yeah, I understand that. I mean, without supersymmetry, they can't do the universe, and that'll be sad. But the one thing here is that why the strong belief? So you see, because this moves millions. This is not, I agree that it's good to figure out if that is there or not and testing a model and so on. But trust me, if I have a model, I'm not going to get the amount of millions that this gets. Even if nothing is found, even the LHC finds, which I'm not saying we shouldn't, I'm just saying there's something to contemplate. Even if the LHC finds nothing beyond the standard model, even if all the super complex experiments for axion detection find nothing, which is what so far we're seeing, even if that's the case, they will still receive millions and millions and millions to do the same thing and test the same models, which is extremely interesting. So what's special? Why do you think it's worth pursuing this instead of something else? No, I mean, I don't know. This is more philosophical. How much our prejudices are loaded into this? Maybe something to contemplate once, even if it's to be told, no, you're not right. These are the good reasons why it is worth still putting that much money in this.
Well, this bumps up against the limits, I think, of my knowledge into like the quantum field theory aspects of the axion, because as you might be able to tell, it's not really necessary to understand any axion theory to do this research in quantum metrology. But from my understanding, this is a natural term in that the CP symmetry violation in the weak force kind of implies that there should be a CP symmetry violation in the strong force or the QCD Lagrangian, because this theta term is actually like a some sort of like geometric mean of the violation in the weak force. And
I understand. I mean, it's a natural term in terms that from what we believe are the first principles we should apply to get the standard model, that term shows up. That term shows up with a constant that could be anything, that theta. If somebody had measured the constant to be 7, or not 7, to be I don't know, pi, then people would not have any issues. But if it's 0, they have issues. See what I mean? If you measure that this constant is pi, nobody would have said anything. Whereas, oh yeah, it's pi. We measured it.
I mean, if it was exactly pi, that'd be natural.
Yeah, no. What about if it's pi minus epsilon? You see, any number is exactly that number when you obtain in the lab.
Right.
That's the point. So I wonder. I mean, I understand the I call it Gelmaniac. That's me. The Gelmaniac thing. I say like, well, look, the probability of getting 0 is 0. But if you do the experiment and measure, imagine I measure 0.3799, and we know it with 9 digits. Mm-hmm. Nobody would have any issues. Measuring 0 to 9 digits is an issue. Now, why is it an issue? It is allowed by the theory for that to be 0.
I mean, so I feel like this is, yeah, a philosophical question into the concept of naturalness, but, you know, where any value of theta has the same, or any, you know, region that theta could fall in has the same probability. It's the fact that we're measuring it to be 0 as compared to any of these other things that we could measure does seem funky, no? No, but here we go, Kelly. Imagine it would be funky to assume a priori, but you do an experiment and the experiment tells you 0.375. Imagine you measure 0.3751199 or whatever. Mm-hmm. And then you say, I doubt your experiment. Why? Because the probability of having obtained that is tiny. And I can say that about any experiment that determines any constant. Feynman has this famous lecture thing that he comes to class and says, you know, today I looked at a car when I was coming into campus and the license plate was BCH 977. What are the chances? You know what I mean? That probably didn't exist because the probability of actually finding that, you see, you cannot talk about probability after the fact. So this is an experiment. An experiment is done and you find with 9 significant digits, you find that it's 0. If you had found any other value, then you would be happy. But why 0 and happy? So this is more philosophy than anything else. It's kind of like in some thermodynamical system, every microstate is equally likely, but I would still think it's very odd if like all the atoms in a room were over on that side, because there are so many other possible microstates where they're everywhere. But that's, again, but Kelly, you see that argument, you are using it against 0. Imagine that you do your experiment and you measure 0.139, something that is non-zero. And then I tell you, oh, Kelly, I distrust it. Why? Because that's like arranging all the atoms in a particular way. Maybe not only on one side, but maybe with holes here, you know, to get this configuration. This is not about the number of microstates compatible with this, right? This is about a fundamental physics constant, which means, right. I'm making an analogy to say that we wouldn't think it's odd if we measure all the atoms in a room to be evenly dispersed throughout the room, because there are, even though every microstate is equally likely, like we can say angle of theta is equally likely, there are much more possible angles of theta or orientations of these molecules where they are evenly spread out, or where theta is something non-zero. If we were to look at all the atoms in a room and find them all in one tiny corner, we might wonder, is there some mechanism that's causing them to all be concentrated in that corner? That's a good argument, but look at the difference, right? An Avogadro number of molecules in a room, certainly the probability of one configuration over the others is negligible. Here, given a value, so if the value is 0.103, let's say that this, if you want relative orientation, which I dislike though, but let's talk about in this terms, the relative orientation of quarks, I hate it. Those are mixing angles, but whatever. These orientations compatible with that are not that huge. They're not really that huge with any value. If you give me a value, the arrangement, maybe there are 3 or 4 of them, 5, maybe 10. But I don't think there are that many. I don't think we're talking orders of magnitude, right? You don't think that there are that many possible values of this angle? Yeah. So you're saying it couldn't be any... For a fixed value of theta, how many different configurations or micro configurations would give you that different non-zero value of theta? See what I mean? I mean, the theta could take any value between 0 and 2. Correct, but imagine you do the experiment and your experiment tells you theta is 0.3. Okay, that's a fact. We take it for granted. Would you trust that, or would you think, what are the chances? That's my point. Why is 0.3 better than 0? Could you explain it fast? Why 0 you still distrust and 0.3 you don't? I would trust 0.3 because it is non-zero.
But that is not enough, right? What are the physical arguments for saying that 0.3 is better? Imagine you use the analogy, somehow probabilistically favored over the zero. I don't see it.
Well, it's the same in my mind with the analogy of some collection of atoms.
How is it the same? That's what I don't see, right? I don't see it here.
I know that I would expect to see atoms evenly dispersed throughout the room and not question it.
I agree. I don't see the analogy. That's my problem. Because here we don't have an Avogadro. We don't have many micro configurations that give the same value of theta, and zero only one. So the analogy would be if we have many configurations, an immense number of configurations that gives theta different from zero, and only one configuration that gives theta equals zero. That's what I don't see here. I think the value 0.3 is as unlikely as zero. That's my point. And I don't, maybe I'm wrong, but I'm not seeing, you see, I'm not, this is my thought. I may be wrong, and maybe something that I'm missing. But I don't see why 0.3 is better than zero.
Yeah, maybe we can talk about this more later.
All right, no, cool. This is again philosophy in the sense that I feel there's sometimes a lot of human prejudice in particle physics and in many other fields of physics, right? That we don't like zero, even though we're measuring zero, which is very interesting. I mean, it's obviously it's not zero exactly. Maybe it's a very tiny amount, but it's indistinguishable experimentally from zero, and then you can call it zero. Or maybe their model is just wrong. You see, these things to me are more likely than the fact that the value is not zero and we need more precision to find it. But I may be wrong. Again, this is a perception. And while I agree that people should still do these experiments, what I may have some doubts about is the amount of resources in physics that we want to dedicate to these searches.
Oh yeah, there's lots of money.
It is. And also axions as dark matter have other problems too, no? They're not like that perfect as dark matter as, maybe we'll not get there because I'm not an expert, but I've heard people giving talks.
I'm not an expert either.
Okay. I've heard people giving talks and say that actions for dark matter may not be, it cannot explain all of dark matter, certainly, maybe a part, but it's definitely not a super solution for dark matter. Anyhow, I love the talk, I love the topic, and I like it, and I really think the experiment is cool. Don't think of this as a comment that I didn't like it at all, or I don't like this field. This is more, I think, as scientists, we should be critical about this, whether.
Yeah, absolutely.
And I don't know if anybody has more arguments, as in like, I don't know. What about the more high energy physics oriented people in the room? I don't know who they are, but. Bruno, what do you think? Bruno, you're the closest. I'm not saying as about Thales.
Am I?
I think so. I mean, you are closer related to people working in high energy physics in the room.
Yeah, well, I think that discussion is the same as the general naturalness problem that plays much of the like anthropomorphic arguments that people draw for several parameters in high energy physics. I think like in the last few years, people have been like criticizing that much more strongly, but I don't have any strong feelings about it myself. So,
right. Anyhow, just something to keep in mind, Kelly. I loved it. This was you're great giving talks, certainly.
Thank you.
This was a very good talk, very good delivery, and very clear stuff for a complicated topic. So very nice.
Good. Glad to hear it.
Any more questions? All right. Well, then let's thank Kelly again. Thank you. I'm gonna start the recording.